Okay. Okay. Hello, everyone. So today our speaker is Selman Ipek from BilTop University, and he's going to tell us about simplicial distributions and polyhedral geometry. And at the end, I think there will be a demo of code that can actually generate some examples of simplicial distributions. Okay, Salman, the floor is yours.
Okay, thank you, Cihan. As you mentioned, I want to talk today about, I will just simplicial distributions and polyhedral geometry. So I think one of the reasons this is a kind of interesting subject is that you kind of mix together things, structures like simplicial sets coming from algebraic topology, and then also you're connecting to these very concrete sort of geometrical objects. I think it's kind of interesting. So just to give a little bit of background, so I think that simplicial distributions are sort of interesting to study, interesting mathematical objects to study in their own right. But one of the things coming from the physics point of view, which is my background, is that, you know, some of the analytical control that you get from these theory of simplicial sets might be useful for actually also computing properties of these polytopes, convex polytopes that appear in these theories and that are of interest in physics. So, you know, we are usually considering, so for example, I just want to remind you guys of some terminology. And so, you know, if we have X is a simplicial set, then, you know, if we have some sigma in the in n simplex, it is called and I can't remember, Cihan, did you talk? You probably discussed some of this degenerate.
In my talk, yes, I defined simplicial sets. Exactly.
Okay,
Yeah.
so people know what it means for a
Yeah,
n simplex to be called degenerate if it's
exactly.
in the image of if sigma is in the image of some Sj, some, I'll just call it degeneracy map. Okay, and otherwise it's otherwise we call it non-degenerate. And then there's this other sort of definition that we talk about. So if sigma is in the image of a degeneracy map, then it's called degenerate. If sigma is not, if sigma is not in the image of a face map and non-degenerate, then it is called a generating simplex. So as you will see, in order to sort of work with simplicial distributions in a very concrete manner, it will be the case that we can restrict ourselves to collections of distributions defined on these generating simplices. So for every simplex, you will have a distribution. Every generating simplex, you will have a distribution. If you had considered a simplex that was in the a degenerate simplex, you can always generate the distribution on that from the distribution on the generating simplices. So maybe I will just informally mention that at some point. And also we know the following, a simplicial distribution. So we have, okay, so maybe there's not so much of a need for saying what a simplicial distribution is, but we typically think of a simplicial distribution as this, where X, Y are simplicial sets. So I want to sort of talk about so Aziz talked last time about a special kind of outcome space. X is called our measurement space. It encodes these compatibility relationships. And then Y, sorry, this should be like a capital. Then Y is what we call an outcome space. And so we have a special example. I will specialize a little bit more. Some of the results will hold for any Y, but sometimes it's nice to be concrete. So if you consider Y equals NZD, well, what does this thing look like? If you recall from Aziz's talk, the N simplices are just N tuples and then we have some face and degeneracy maps. The face maps are as follows. So if I is equal to the first one, then we actually just delete the first one to AN, I equals 0. If it's between 0 and N, so it's A1, AI minus AI plus 1, all the way back to AN for 0I. And then if it's I is equal to the last one, then we delete the last one. A1, A minus 1, I equals to N. And for completeness, if we have A1 to AN, then this is just equal to A1 AJ minus 1, 0, AJ, AN. So the degeneracy map just adds a 0. So I want to introduce this just to also talk about what do the space of, so we had this simplicial set D, in this case, NZD. So this is also a simplicial set. So the n simplices of this are going to be distributions going from Z D to the N to, I will just restrict myself to the non-negative reals. For our distributions, it's more general than this, but I will restrict myself to actual proper probability distributions. We have, so face maps, A1, AN minus 1. Because I think Aziz maybe talked about this slightly, but I don't remember if he also included this simplicial set.
Yeah, I talked about this. Yeah, right. But okay,
You did, Aziz? If I can skip
Yes,
this,
yes.
that would be okay with me. So I will just one thing that I wanted to add just in passing was that if I have a degeneracy map acting on P, A1 to AN plus 1, then this is sort of going to be useful to think about intuitively. So what you have is that if I take a degeneracy map of P, what it gives me is a proper distribution from ZD to N plus 1 to R, but those probabilities are determined already by A1, AJ minus 1. J plus 1, N plus 1. So AJ equals 0. Sorry, that's a little bit messy there. 0 otherwise. And so the just thing that I want to say here is that we have that the degenerate simplices for this simplicial set are determined by the lower dimensional ones, just as we did before. So that sort of is going to motivate what I said before, that we're only going to need to restrict ourselves to studying simplicial distributions, the collections of distributions on the generating simplices. So maybe just say it as a remark. Suffices to attention to P sigma of A where let's see, sigma is generating. So what we want to sort of discuss is, so if we have that sDist xy is the set, okay, be the set of simplicial distributions p x dy. Okay, so that's, I don't remember if you guys used this specific notation, but I will just use this one. sDist of xy is the set of all simplicial distributions from x to dy. And so our goal here, so maybe I will just say, is goal is show that sDist of xy is a convex polytope. So I should also say that x and y, I guess they have to be finitely generated. That's the lingo, right?
Sorry, can you say it again?
Yeah, so for this statement to be true, x and y, they need to be finitely generated. This is what, okay.
I think, so I think the correct statement just possibly requires X to have finitely many non-degenerate simplices.
Finitely many
Yeah,
non-degenerate simplices. Gotcha.
I think that suffices for this to happen. Yeah.
Okay.
To be polytope, right?
Yeah,
To be
that's what I
convex
mean.
sets
To
and
be
solvents.
polytope.
Yeah. Yeah.
Thanks. Many non-degenerate so okay, very nice. Thank you guys. Okay, so a little bit of a background primer on polytope theory. Just some basic definitions, because to give away a little bit of the punchline, the way that we will see that simplicial distributions are convex polytopes is that naturally these simplicial distributions are given in their H representation. So, just I think that maybe what will follow might seem like a lot of detail. It's just a very straightforward thing. When I have a simplicial distribution, I have collections of probability distributions. Each of those probabilities need to be non-negative. This is an inequality. And then every time, so for it to be a distribution, each distribution needs to be normalized. So this is like you're cutting the space in an appropriate way that I'll make very clear. And then also every time you have these compatibility relationships to say that this simplex and this simplex, they agree on their face, that introduces additional constraints. These are linear equalities. And so you will actually find that you have a space that's given as the intersection of finitely many half spaces. These are the inequalities, and then you're cutting them with these these hyperplanes. Therefore, you will get a polytope. So all of that is just to say that everything that I'm going to say that follows is basically just formalizing this. But intuitively, I think that it's already kind of clear that these will be polytopes. So so when we talk about a hyperplane, I will say it's like some h equals 2. So it's all the points in Rn such that a dot x equals b. And so this is an affine subspace of dimension n minus 1. So then we also call, I guess I use just regular h here, h plus. So this is a half space. So basically, I'm going to consider a related inequality. So these are all the x's such that a dot x greater than or equal to some b is called a half space. A half space corresponding to half space inequality, or just inequality ax greater than equal to b. Okay, so then we have that an H polyhedron what is an H polyhedron? It's a subset of Rn given by the intersection of finitely many half spaces. So we have P is equal to all those x such that ax greater than or equal to b. We're now in a little bit of an abusive notation. The b is now a vector. So here, this is a matrix of inequalities. Say I have m of them, then this is an m by n real matrix. And then b is m. So just I have m of these, and I guess this definition is sufficiently general that I can also include equalities, say something like ax equals b as being ax greater than or equal to b, ax less than or equal to b. So this H polyhedron covers cases where you also have these equality constraints. You just have to make this it's maybe a little bit clunkier to do it that way, but it will just make the presentation a little bit more streamlined. So when I say ax greater than or equal to b, this could also have these equalities defined in there too. Okay. So just some basic facts and definitions. Okay, so I will just rattle these off, and please let me know if one of these does not seem reasonable. H polyhedron is convex. You will see that there's another definition, another representation of a convex polytope as the convex hull of finitely many points. So in that representation, it's clear that the polytope is convex. H polyhedron is convex. It's not hard to show it. If you take some space, say P is a polyhedron, and you intersect it with a half space, or just, sorry, a hyperplane. So then you have that this is also H polyhedron. This just follows from the very definition that we used. If you just introduce another hyperplane, then it will still follow that definition. So a convex polytope is a bounded polyhedron. By the way, I will often just say polytope instead of convex polytope all the time. We will not be dealing with non-convex stuff. Here bounded, I can say it, but I can also just say it contains no ray. It's you know, if you have a picture in your head, obviously, you know, something like something. Oh, okay. So if I just take a coordinate system, 2 dimensions, if I just have the following inequalities, you know, like x greater than or equal to 0, y greater than or equal to 0, then I have this this unbounded H polyhedron. It's just the positive quadrant. And then, but this is not a polytope because I can always find a ray. Sorry, this is, well, yeah, so, and then if I define something like this, sorry. For instance, this is bounded in the sense that there exists no ray that goes off to infinity, that it contains no such ray in it, therefore it's bounded. That's what we mean by that. Okay, so some other things that I will just be freely using. So what do I mean by the dimension? Dimension of a polytope is the dimension of smallest affine space that contains it. So I will need this to define the notion of a vertex in a sort of algebraic way. Okay, so what do we mean by this is a V polytope. So this is the other representation. So imagine that we have a set V I equals 1 to, say, little n. So I have a finite subset of Rn, so it's a finite point set. Then I have that a V polyhedron is precisely the convex hull of P. Is this okay? When I say this, people are comfortable with me saying, I think the Aziz defined convex abstractly before. Here, this is a much more concrete definition. Just for any 2 points in the polytope, you also contain the convex line between them. So it suffices to restrict our attention to the extreme points. Okay, I think this is okay. Okay, so this is the main theorem of polytope theory. So if you look at a very well-cited book like Ziegler's Lectures on Polytopes. There's an entire chapter just on the Minskowski-Weyl theorem, and they don't even always call it that. It's just the entire chapter of the book is called the main theorem of polytope theory. So this is what it is. It's basically just saying that a subset P Rn is convex hull of a finite set. So P is equal to a V polyhedron if and only if it is the bounded intersection of half spaces. So okay, so I mean, there are some examples that I can just sort of, I mean, these are almost trivial. It's not even worth including them, but just to make the point clear, when we have something like the cube, let's make it look a little nicer than that. Okay. Here, we can sort of describe the cube in two different ways. So you have this V definition, which is I basically have these extreme points. So I will take this to be my origin. So you have like 0, 0, 0, and then 1, 0, 0, 0, 1, 0. Like, for example, this is 1, 0, 0. And let's see, 1, 1, 0. And then there's some more. There's 8 in total. This is what I described was just the bottom ones here. And then you also have the ones up here. So there's another 4 that come from there. And then the H representation is just saying the following, that I have x coordinate, y coordinate, z coordinate greater than or equal to 0. And also minus x, minus y, minus z greater than or equal to minus 1. So I wrote it in what seems like a weird way. This is just x, y, z less than or equal to 1, but I wrote the inequalities up here in a particular way, so I just want it to be consistent. So, and then maybe I will also include this one because it's not full dimensional. So I didn't describe that term, but so when I have a simplex, which is something that we deal with when we have simplicial distributions, although this example, I'm not sure if it shows up. Maybe if the outcome space is S1. Anyway, so if you have something like this, and the V representation of this simplex is going to be precisely, there's going to be 3 points. So say 0, 0, 1, 0, 1, 0, 1, 0, 0, something like this. Whatever, I will write them. 0, 0, 1. 0. And then, so, okay, but one thing that's a little bit different here is that when I write the H representation, I have not only that the coordinates x, y, z are greater than or equal to 0, I also have the following equation, which is that x plus y plus z equals to 1. So I could, for example, solve this by saying z is equal to 1 minus x minus y, and that will give me this two-dimensional subspace right here, which is not filled in behind it. It's just a two-dimensional hyperplane in this case. Okay, so we can move on. Okay, so I will just say the following. The set sDist of xy is a okay, so let's see how this works out. I'm just going to basically repeat myself from before, which is just that it's not hard to see that this is a polytope now that we know what the definition of, for example, an H polytope is, because if we have simplicial sets x, y, where it's n simplices are sigma n or omega n, so I will write it like this. So for each generating simplex, we have the following. We have, for each generating simplex, we have that P. So if I had a simplicial distribution, maybe I should have said that. Just, you guys know what I mean by simplicial distribution here. I will add it for completeness, just like this. For each generating n simplex, we have the following: P of sigma n of omega n. So this is just each probability that occurs on. So in some sense, we're choosing a natural set of coordinates. The number of the ambient space that we're going to sort of embed this polytope in is going to be the total. I will do this in quotes. The total number of probabilities on the generating simplices. So it's probably possible to count this explicitly, but it will be a little bit messy in the general case. So I will just sort of leave it informally, but I think you guys understand what I mean. Take each generating simplex, take the outcomes, however many the outcomes there are for the outcome space, and you enumerate all the possible probabilities. And each of those need to be greater than or equal to 0. So this defines already an H polyhedron. So this is like so this is like positive, I guess maybe orthont of some. By some, I just mean that we've chosen n to be precisely the number of probabilities in the way that I described it before. So we already have that this is an H polyhedron, but it's not bounded. So we also need to impose normalization. So that is to say, for each generating sigma n, we have that over all possible outcomes, P sigma n omega n equals to 1. So this forces each P of sigma n omega n to be in 0 to 1. I think that's pretty clear. So this bounds the coordinates. So now we actually have that we have a convex polytope. So the next thing is the compatibility slash sig thing. So in general, this will be, let me think of how I want to say this. Let's see. So the compatibility, non-signaling relations, it will be easier to just sort of write them eventually, but I will write this in quotations. These are going to be something like a sum, and we have to, this is why I'm putting the quotations, but you have sigma n. So if I have two, okay, maybe it actually helps to be just a little bit more nice about this. So if I have that two simplices, sigma n, sigma m are generating, so sigma n is an n simplex, sigma m is an m simplex. So there's a compatibility relationship. If we have something like this, I1 d I k sigma n is equal to dj1 all the way to djk prime sigma m prime. I will put a prime there. So that imposes some sort of relation on my probabilities. It will be like di1 dik acting on p of sigma n, and the outcomes will be on the n minus k outcomes equals dj1 djk prime of p of sigma m prime omega. I guess it should be the same, so I will just write n minus k again. So what does this amount to realistically is that maybe if I go up just a little bit, you guys will remember what the face maps. Oh, did I not write what the face maps were? I did not. But last time Aziz told you that the face maps are essentially sums. So when I take a face of a probability distribution, it's like marginalization. So what is marginalization? It's a sum over an appropriate domain of probabilities. So when I impose something like this, it's going to be, and I will put it in quotes just to avoid having to be very precise, but it's a sum over P of sigma n omega n equals sum P sigma m prime omega m prime, yeah. Okay, well, as long as we're not being precise, but I will give an example to make it a little bit more clear what I'm talking about. Essentially, though, the punchline is that because this is something linear in P's, we have essentially another constraint equation like this, which is going to bring us down into, which is going to cut the polyhedron into a smaller space. So maybe I do some examples now. Any questions? You guys have not really yet. I didn't look to see if there's any questions in the chat. No, I think it's okay. Okay, so. One moment. Okay. So there's some very basic examples that we can look at. So if I have just, maybe I say it here. If we have like x is equal to 2 simplex and y is equal to nz2, then we often write our distributions in the following way. It's just a convention, but it sort of helps. So I will write it like as follows: 0, 2, and then maybe something like I suppose I don't actually need to. A, B are going to be my bits, so my distribution here will be over Z22 because there's one non-degenerate. There's in fact just one generating simplex, the 2 simplex. So here I just have something like this. And so what does the polytope look like for this thing? It's going to be something like P of sigma of AB greater than or equal to 0. Well, how many coordinates are here? There will be 4 coordinates. There's 4 possible outcomes. And then there will also be a sum over AB, P sigma of AB equals to 1. So the dimension here will be something like 4 minus 1 equals 3. In fact, we can draw this. I think. It will be something along the lines of it will look a little bit like the previous picture, but I don't want that to be deceiving. So it will be something like this, and it will include the origin. So each of the vertices of this thing, so if you remember, the simplicial distributions on the simplex are always non-contextual, and what that means is that the vertices will be these deltas. So delta 0, 0, delta 0, 1, delta 1, 0, delta 1, 1, and this whole thing is going to be filled in because it's a 3-dimensional convex polytope. So we can give another example, but it will not be possible to visualize it. So perhaps we look at x is equal to something like this. And we will keep y, the outcome space, the same. And so now what will we have? Same picture, just in terms of, I will put the probabilities in each of the P sigma. So let's call this sigma, sigma prime, AB, P sigma prime, A prime, B prime, something like this. So how do we construct the polyhedron for this one? So we have, again, P sigma of AB greater than or equal to 0 for every A, B in Z2. We also have P sigma prime of A prime, B prime, greater than or equal to 0 for every prime. Okay, so that's already embedding us in a space. We will embed our polyhedron in a space of R8 for each of the four. So this is 4 times 4 times. So our n in this case will be 8. Then we will have normalization. So sum P sigma AB equals sum AB, A prime, B prime, P sigma prime, A prime, B prime equals 1. So that's 2 constraints. And then we will also have a constraint coming from, in this case, the non-signaling or compatibility. So if I choose my orientation to 1 prime, D1 sigma equals D1 sigma prime. This implies that I have equations like this. P sigma 0, 0 plus P sigma 1, 1 equals P sigma prime 0, 0 plus P sigma prime 1, 1. And then there's another one like this. P sigma 0, 1 plus P. Something like this, just for completeness. So in fact, these are not all linearly independent though, because once I impose this one, I get this other one just from the normalization. This is like 1, if you just do 1 minus this expression. So yeah, we don't need both of these. So here the dimension will be 8 minus 2 minus 1 equals 5. So what I want to say here is, this is a little bit of the goal sometimes. So we will call the polytope, so let P of X, Y be P of X, Y is given in H representation. We want to find its B representation. That is, we want to find the vertices such that for any simplicial distribution P, let's see, we want to find P of X, Y as equal to the convex of some finite point set V, such that you can take any simplicial distribution now, and it will be able to be written as I equals 1 to some chi of lambda I VI, where VI is coming from this finite set here, where lambda I okay, so just convex. So any simplicial distribution can be written as a convex combination of its extreme points. So it will be interesting or useful to be able to enumerate all the V's that are in this set, so that we can. This will give us the ability to analyze the space, the convex, the space of simplicial distributions. So what does that entail? So what that means is we need to have a definition of a vertex. So okay, or rather first, what is a vertex? Okay, so there's two definitions. I think one that Aziz uses a lot is like a geometric one. I will call it geometric. So V in PXY is a vertex if and only if, because I'm lazy, for all X, Y in PXY, the solution to V equals, I will say lambda X plus 1 minus lambda Y is V equals X equals Y. So what is this one saying? This is like, I have something like this, and if it's a vertex, it means I just cannot write it as the convex hull, as being in the convex hull of any other 2 points. So this is kind of the picture that we have in mind. So this is V. And you can see that the only way to write it as a convex combination would come from points that are outside of our polytope. So the other one that is a little bit more suitable generally for algorithmic stuff is the algebraic definition. V in PXY is if it's going to be a vertex, it must be the unique solution to D inequalities satisfied with equality. So what do I mean by this? If I go back to this cube example, the cube is a good one. So if I go back to the cube example, what exactly is a vertex? So let's pick maybe this one. So a vertex, if you see it, I have a set of, okay, I have a set of equations. So these inequalities here, I have something like z is less than or equal to 1. So I will just write it like that. I have, or maybe this is I will actually look at this 0 point. So what are the inequalities there? X greater than or equal to 0, y greater than or equal to 0, z greater than or equal to 0. Now, if I set these each to equality, x equals 0, y equals 0. I mean, the solution here is almost trivial, but if I set these inequalities and say that so I have a 3-dimensional space. So if P is a D polytope and I set 3 linearly independent inequalities to equalities, then and I get a unique solution, then that's a vertex, roughly. I probably needed to say, okay. So by the way, I made a mistake here. This needs to be a D polytope. For this definition to hold. Is this okay? Does this make sense? Okay, so maybe I will write it a little bit more. So suppose I have a P polyhedron given like this. By the way, how much time am I supposed to have? Is it till 2:30 or is it till what time? till 3 or till 230? Yeah, I'm guessing 3 is okay. Okay, so if I have something like this, Rn, and then I have a set of inequalities like this. I want to say that I have m inequalities. Say. I want to define, so I'm just trying to be a little bit more specific about what do I mean by having a vertex. So define Vz. So if V is a point that's in the polytope, define this set I in M. So what is this notation? This is the set from 1 all the way to M, such that I is in the set if AI, the ith inequality, V is equal to B. So, and this, the number of elements in here could be greater than D. So this is if V is a vertex. So it has to be greater than or equal to D. And then what that means is that for all such elements in there, okay, then there exists some subset of V such that AI1 V equals BI1 all the way to AID V equals BID. And I will write this in terms of a matrix like this. ZV V equals. So what is this box notation? It's just saying I'm taking the subset, the rows for which the equalities on the left-hand side hold. And then this matrix must be invertible. So basically, I have this set here. This set could be greater than or equal to D, but I'm looking for this just regular Z subset is a subset of D indices such that the corresponding matrix AZ is invertible, so that we have this unique solution. Like that. Okay. So what does that correspond to with simplicial distributions? Okay, I will do a couple of examples. So perhaps you guys noticed that when I set these inequalities to equalities, for us, what that means is P sigma of omega equals to 0. That's what it means for, so I will write that not here, but so for simplicial distributions, we have that for an inequality to be an equality, it means that for some sigma and some outcome, we have that the probability is equal to 0. So let's take this example of the 2 simplex again and outcomes in Z2. So we have P00, P01. Okay, so first thing is we have, as I mentioned before, we have PAB greater than or equal to 0, sum AB PAB equals to 1. to find out what the vertex is, we need to find out what is the dimension. So here, as I maybe mentioned in the previous example, P of X, I will just call it, is equal to 4 minus 1 equals 3. So in order to find a vertex, we need to be looking for setting 3 of the 4 inequalities to 0. So you can already see how the simplex is non-contextual, because what is happening is I say pick P00, maybe I use this notation, P00 equals P10 equals P01 equals to 0. That's what it means to set. So if the dimension is 3, I have a 3 polytope. I need to set 3 of my inequalities to equalities. So that's what will happen. And then I will have this table. And it just means that I set some of these to 0. So what is it? I set 0, 0, 0, 1, 1, 0, so that this, I have a precisely one solution to this, which is this distribution. And this is what we call a deterministic distribution. I'm not sure if Cihan went over that before. I can't remember. But as you might be able to see that if I need to set 3 of these to 0, how many possible choices are there? There's 4, choose 3 equals 4 choices. 4. And they will just be something like, maybe I draw them here. So I have 1, 0, 0, 0. 1, 0, 0, 0. 1, 0, 0, 0. And 0, 0, 0, 1. So there's 4 possible choices. These are the choices. These are all the vertices, and they're all deterministic in the sense that only in each distribution, only a single outcome has non-zero probability. So that's the only one that will occur. So anything that's in a simplex will be non-contextual. It's just the convex hull of these deterministic ones. Okay, another example. Okay, so let's call this sigma. Let's call this sigma prime. So I have two simplices glued along a single edge. So I have P sigma 0, 0, sigma 0, 1, P sigma prime. Okay, so what are the equations for this one? P sigma AB greater than or equal to 0, P sigma prime, say RS, greater than or equal to 0. Okay, so how many possible coordinates do I have in this case? There's 4 plus 4, there's 8. Then you have the normalization, AB, P sigma AB equals RS, P sigma prime. Okay, so that lowers our number of dimensions by 1 each. And then we also have the one that I mentioned before, D1 sigma prime implies that we have this equation, P sigma 0, 0 plus P sigma 1, 1 equals P sigma prime 0, 0 plus P sigma prime 1, 1, with the other equation being determined by normalization in this one. So we had again that the dimension of this polytope is 5. So now what I need to do is find 5 zeros in order to find a vertex. So say that my strategy for finding a vertex was just randomly setting certain inequalities to 0. Let's see how well that works. It's not always the best way to do it. So maybe I will put one right here. Okay, so say that the ones that I picked were precisely like the following. So let's go like this. Say I pick 1, 2, 3, 3 zeros, and another 2 zeros. What does the distribution work out to be? So in this simplex, normalization requires that I have to have this one be 1. But on this second simplex, if I make this one lambda, which is just some non-negative parameter, then this other one is 1 minus lambda. So it is not a unique solution. So something went wrong, and what went wrong is that these zeros are not linearly independent. Essentially, what happened is if I choose P00 and P11 to be 0, then it requires automatically that these are 0 from this equation here. So choosing these two to be 0 at the same time as this is not an independent equation. Choosing this one and this one is independent, and then this one is forced. Or yes, I think more or less. So a different one might be if I chose like if I chose 1, 2, 3, and then instead I chose sorry. Oh yeah, this one and this one. Okay, so what happens now? This one is still 1. This one requires, we have an equation here. So that one, sorry, there's something wrong there. This is still 0. But now this one is forced to be 1, but this is a unique solution. So this one is in fact a vertex. And in fact, maybe Aziz will prove this next time. Fact, diamond is always non-contextual. So it's going to be the case that no matter which way we solve these 5 zeros for this case, it will always be a deterministic distribution. So that is, the probabilities will always be 0 or 1. And so we call that non-contextual. And so there's a sort of deeper underlying reason that comes from gluing. So if you tried to doing this in an algebraic way, it would be very time consuming. I mean, even though, I mean, you can do it by hand for this case, but the diamond is always non-contextual for any outcome space Y. So here we did it for n equals Z mod 2, but you could do it for any Z mod D, and D could be as large as you want. So all of a sudden the polytope could be quite high dimensional, like D squared dimensional, minus some constraints, but it will still be non-contextual due to gluing. So that's the power of some of the stuff that we're able to get from the simplicial sort of set approach. So I think that I will do a little demonstration. We have a code for some of this stuff. So that's actually just the end of the theory part. I mean, I didn't go into the algorithmic sort of side of how people find these vertices in a sort of more efficient way. I would be happy to. I mean, if there's some interest doing a talk like that, it would not be very, I don't know how simplicial set oriented or it would be. It would just be more about the, more general tools that people use, but I'm open to that. So I can also share my screen here. Any questions before I will move on to the demonstration of our code?
Okay, I think you will leave this page, right? So maybe
Yeah, so I was about to say that the main sort of picture that I want people to have in mind is this like this one, for example, this diamond one or this simplex. I want you guys to sort of have these in mind if possible, so I can when I'm going through the code, you see how the construction in the code mirrors the actual sort of geometric figures we have here. Okay,
Okay.
but I will leave this page.
Yeah.
Can you see the new page or do I have to?
Yeah, we see your browser.
Okay.
Yeah.
Okay, so maybe I didn't show you guys. Cihan, do you want to link? I don't know if I will be able to.
I'll find it. I'll find it on send it.
Yeah, so it would be good if you could link the actual page. So this is under BilQCT GitHub repository, and I think the repository's name is just going to be 2dim. And in 2dim, we restrict our attention to two-dimensional simplicial scenarios. What do I mean by that? So the measurement space X has to be two-dimensional. In fact, the outcome space is restricted to the nerve, but it can be up to nerve Z mod D for any D. So okay, I mean it's so this page that I'm going through is readily available. There's some background on the simplicial sets and probably restricted to the two-dimensional case. Here we have what looks like just some more of the stuff that I mentioned today. Yeah, I didn't talk about these edge coordinates, but for Zmod 2, there's a special sort of coordinates that embed so that we have our simplicial distributions embedded precisely. If it's a D polytope, it's in D-dimensional or RD rather. Okay. And then there are the conventions. So I don't know if I will go into some of the more exotic cases, but so suppose this is a single triangle with two edges. Let me skip that one for a second. Let's go to the diamond first. So this is the two simplices glued together. So, oh, sorry. Let's see. Okay. Let's see if I can make this bigger. Okay. And maybe I can get this out of the way. Okay. So the diamond scenario is going to be two triangles glued along, in this case, just the D1 face. It's precisely the same picture that I had before. So what do you need to do? You can identify the four vertices. In fact, the vertices can all be identified usually. It doesn't really matter too much because what sort of matters is the face relations up until the one faces. D1. Okay, so these are now the edges. So how do we index these? So you give a sort of ordering to the edges defined by, so you just identify them and then also the faces. So the first edge is going to be the D0 face. The second edge of the first triangle is going to be the D1 face. The third edge of the first triangle is going to be the D2 face, so on and so forth. And then we have D2 is the set of two simplices. This one is going to be, there's one where the vertices are, the 3, 2, 1 in this case, the way that it works out. And then you just bundle the entire simplicial set into one sort of list. And all you have to do is run. So I will, let's see, I forgot to run this. Okay, so it shouldn't take too long. So I will cut this out for a second. Okay, there we go. So we just ran it. So in this next bar, instead of computing this one, which we haven't talked about what the edge coordinates are, I will compute 2dim like this. So this is now computing the vertices of the polytope. So let me go into a little bit of what's happening here. So field names of 2dim dist. So I have an object here, 2dim dist, which I input my simplicial set and my outcomes. So in this case, I'm restricting to outcomes Z mod 2. This object has a couple of different properties. One is the inequalities for, so let me, just to give you guys an idea. So 2dim dist. And if I want to see the inequalities that define this polytope, these are my 8. So the 0th one is just saying that these probabilities are greater than or equal to 0. And then the 9th row is kind of just an ancillary role that never really means anything. So these are the inequalities. And then also we have the prob equations. So these are the affine equations so normalization and the non-signaling. So you can get those from here. And then if you just want to see the polytope object, which is coming from a program called polymake, you have that it gives you these equations, the inequalities. And then if I want to compute the vertices, I go as follows. So you have to apply the vertices command to the polymake object for it to work. So first you go to the polytope object or the polymake object, and then you hit vertices. Or you could hit, for example, facets, and these are just the inequalities and such. Okay, I think that's what I wanted to say about that. Okay, so we also have the possibility of finding representative vertices. So these are vertices that are in the same orbit under this symmetry group that's called the combinatorial automorphism group. I mean, basically, it's just computing. You can find this symmetry. It's just the automorphisms that map the polytope into itself. So up to the action of the symmetry group, we have one per orbit, which is expected because when you look at these vertices, they're all very similar. In fact, they're in the same orbit. Okay, and so we can even do this for raising the number of outcomes. And you see that again, there's just one orbit. Maybe I can even do 4 or 5. What this is telling me is that the vertices of the diamond are always non-contextual, even as I raise the number of outcomes. You see it's starting to slow down. Let's see. And it still runs up to 7. I haven't really gone past this before. But you can do some more exotic things. For example, if you have a single triangle with 2 edges identified, you have the 0 simplices. I just sort of identified them in this example. The number of non-degenerate 1 simplices. So because I've identified 2 of the edges, there's only 2 of them, as so. And then there's just 1 2 simplex. So I can run this. And for example, if I run the vertices,
بقول لي بتأسف عليه.
what's that, Aziz? Oh, okay. You can see that not all the vertices are non-contextual. If that was the case, it would just be ones that were like this. So if I was to run this representative vertices command, I think I can do this. Okay, give the wrong answer. That's not good. Okay, but that's not really something that I can help. This is coming from polymake. Sometimes it makes mistakes like this. It's a little bit surprising. Let me think. That's interesting. So what if I call this P? I wonder. Okay, so as you can see, okay, and let's just write P here. See if that, no, it's still messed it up. Okay. Anyway, so that's sort of a crash course. If anybody is interested, by the way, if anybody is interested in sort of more computational or algorithmic sort of group theory or stuff like this, you see that polymake did not get the right representative order vertices. There are these algorithms. I don't know if we could maybe write them up from scratch. Maybe they would be a little bit better for our use case. Or other sorts of implementations, feel free to contact me. I'm sort of interested in that kind of stuff too. So maybe we can improve on this.
Yeah. I have a question, Salman.
Yeah.
Do you think we can do to get something in computer that we can get the inequalities in the way that we like by edges or by some simplices like that we want? You know what I mean? You know what I mean, I think. Yeah, right.
Yeah, I think so. When you look, when I give you an example, like let me see. Yeah, so this is the diamond, right? So this diamond is in terms of simplices already. So it's you have to order the simplices, right? So you have to pick a convention, unfortunately, but that's the way to do it.
Yeah.
So here, this is the first simplex, the first four coordinates, and then this is the second four. Okay. If you want edge coordinates, then I can do that for Z mod 2, for example, here. If I run this one, and then, so this one is not the coordinates that you like, Aziz, but they're related. So here we have how many coordinates? This one is, don't worry about the one. There's 5 coordinates here. This is for each of the edges. Instead of -1 means 0 and 1 means 1, it's like that. But I can also map this to, I can also define a mapping to the coordinates that you like in terms of the marginals instead of, these are expectations.
Really? Yeah.
Yeah, so if you just put in this two-dimensional simplicial set here, and you compute the edge polytope, the vertices will be given, these are the coordinates, and they're given in this order. These are the one simplices. So the 1, 2, 3, 4, 5, exactly in that order.
Okay, I understand. Thank you, Sam.
Okay, any other questions? I think this is only for the code maybe at this time.
No, I mean, it could be for either.
Yeah, so our goal is to improve the code for higher dimensional simplicial sets, right? As well.
So I can say something a little bit about that. So I am able to, I have a code that does this for more simplicial sets, ones where there's the simplices are sort of more or less, if it's like a simplicial complex, then I can still do all of this.
Oh, you mean the simplicial complex code we have? Oh, I see. Okay.
No, not that one. It's a little bit different. But if you give me a simplicial set that's sort of like equivalent to a simplicial complex, I can turn it into a code that's a format that's exactly like the one here. So it gives you the n simplices, the n minus 1 all the way to the 0. And then I can find the distributions on that.
Okay.
But
So
the problem is that if you have n simplices where n is greater than 2 and such that it's like not a, so for example, if you have one of the faces be degenerate or something, then I can't really handle that situation.
oh, okay, I see. I see. Okay, so
For
it is.
that, you need to probably introduce your simplicial complex code to do that.
Oh, I see. So you don't have collapsing. I guess that's the
Yeah,
difference.
that's it.
I see. But you oh, I see. Okay, we can discuss this. So I think you are then encoding it in a different way than a simplicial complex representation, I suppose.
Yeah, so my code just, if I give you it in terms of a simplicial complex, I can turn it into a format like this.
Like the one here.
Yes, exactly.
Okay. Okay, interesting. Yeah. So, well, I mean, you can always include the collapsing conditions by hand, right? Right, like in the simplicial complex code. I think that can be extended though, right? So to include the collapse.
Yeah, so you would be introducing some equation constraints, right?
Yeah.
Yeah,
Okay.
yeah, we can do that.
Yeah, I guess in general, the hard part is somehow. Oh, yeah. So the hard part is the number of degeneracies are more in higher.
Yeah.
But anyways, in principle, it can be done, right? So
Yeah, in principle, it can be done. Now, yeah, so we can think about it. I would be interested in implementing that at some point.
okay, sounds good. Any other questions, comments? Okay, I think we had a full 90-minute talk, and it was great. Thank you so
Yeah,
much.
thank you for giving me the 90 minutes.
No, I think it's worth the code part is also very interesting. So this is public, so everyone is welcome to play with it. So anyways, okay. Well, I think this is the end of the session. Thank you very much, everyone. See you next week. But the next week is Tuesday, though, right? Aziz, oh, maybe Aziz is left. Maybe he's left. Okay, yeah. Next week is Tuesday.
Okay,
Okay.
so as is though he knows that he's supposed to talk about extension and gluing, right?
I told him I don't think there's any other thing, right? We discussed this, so I'll remind him the gluing and the extension. But
Okay.
I don't see him here. I think he left. So yeah, that's fine.
Okay.
Yeah. All right. Okay. See you, everyone.